Okay, in this video we're going to be looking at how we can do some relational algebra statements with more than one table. Initially, we're going to look at some of the relational algebra operations that come from set theory, and then we're going to look at how we can use joins for tables. Okay. You will need, I would recommend you have this relational algebra operators handout open again, and then I have a little handout called join tables examples, and in here we've got a couple tables, and we'll be using these for a couple of the examples we have. Okay, so you might want to have both these open so you can take a look at them. Alright, the first operator we're going to look at is union. Okay. And the union of two tables is defined as the set of all rows belonging to the first table or to the second table or both, with any resulting duplicate rows deleted. Okay. So you just take rows from each, combine them together, any duplicates, drop them. Okay. It is a binary operator. You can see the syntax here. We have two relations in it, and there's this big U looking symbol. That is in these relational algebra in the operator handout that I have for you. And I'd recommend you use that. It is also an associative operation, which means if we would union R and S together and then union it to T, it's the exact same thing of doing S to T and then union an R. Now, one of the major problems I see with students using union, intersection, and minus, when you use these, all of the relations that you use in your statements, they must be what we call union compatible. Okay? That's when both relations, they have to have the same type of tuples. In other words, the corresponding attributes in each table must come from the same domain, right? Well, and since we can't totally enforce that within a database, we just say it must have the same data type and the same length. Okay? So it makes it tough if you wanted to do, you couldn't union employee to department. Now you could project the social security numbers from both and union that together, but you just couldn't say union employee, employee union department won't work. Okay? Because the corresponding attributes don't come from the same domain. And what do we have here? 4, 5, 6, 7, 8, 9, 10 attributes in employee and only 4 in dependent or department. So they're not union compatible. Like I said, this is something that I see probably 20 to 30% of the students every class, they don't take this into account when they're going to do a union operation. All right, so let's go ahead and look at an example of this. All right, I want to write the relational algebra that will do this. Okay. We want to retrieve the social security numbers of all employees who either work in Department 5 or directly supervise an employee who works in Department 5. So if we look at that employee table, if we get an employee in Department 5, we can get their social security number, but we can also get their supervisor's social security number. Okay? So it'll be those two attributes that we're going to be working with. So let's see what we'd have to do this. Oh crap, let me put it on the page. Okay. So here we've got the statements that'll do that. All right. So initially, I've got to select from the employee table those folks that are working in department number 5. Okay. Then, from that result, we go ahead and project the social security number. And then from this result, we project the super SSN. We go ahead and union those together, and then we will have a list of folks that either work in department number 5 or they supervise somebody in department number 5. Okay. And the results from the second line here, what's going into result 2, will look like this. Okay. They're the employees that actually work in department number 5. Okay. We want to see who the supervisors are. There's the supervisors of the employees in number 5. There we can see, I believe that's Franklin's Social Security number. And we've got 888-66555. If we look here, that is James's Social Security number, and he works in Department 1. But that's okay because James supervises Franklin. And that's what we want to get, the people that supervise those folks as well. So in the end, this is what we're going to end up after the union. Right? It will be this list of Social Security numbers. Right? We've got them all in there. Notice when we just did the select that we had duplicates of Franklin's number there. And if we had union them together, okay, we could have, 4 copies. But the union doesn't produce duplicates. It deletes the duplicates. Okay? So that's what's happening here. We're getting rid of the duplicates, and we just get a list of those folks. If we want to see that run in SQL, I'll have to open a new window here and bring over the SQL. So this is how we would have to do it in SQL. Okay, so we're selecting the Social Security number from employee where the D is equal to 5. And then we're getting this super SSN from employee where the D is equal to 5. And we can go ahead and run this statement. I got the wrong database selected. Okay, and now let's try to run it. And there we go. There's that list of Social Security numbers. And that's all 5, including James's there at the end. Okay. So that's how the union operator works. Okay, and the next thing we're going to look at is the intersect. Okay, now we're going to look at the intersection or intersect operator. Okay. It is also a binary operator. Here you can see the syntax. A relation, there's the intersect operator itself, and then another relation. In the relational algebra operators, there's the symbol for it that you can copy and use in your statements. Okay. So it is also similar to the union. It is an associative operation. If I can get my cursor in the right place. Okay, so if you intersect R and S and then intersect T, it's the same as intersecting S and T and then intersecting R. Okay. Like the union operator, it also requires the relations to be union compatible. Okay. And please keep that in mind because, like I said, I see more students make that mistake than anything else. All right. Now, let's look at a quick example of this. And I'm going to use the join tables example. All right? I'm going to look at these. And what I want to do is find the rows that are common to both. Now, these tables themselves are union compatible. We've got A column, B column in both, and they come from the same domain. Okay? So let's look and see. So we're looking for the rows that are the same. This is what it looked like. Okay, table A intersect table B, and we will get the results. If we want to see this in action in SQL, I've got it here. Now this intersect operator was just added within the last few months for MySQL. And if you notice, I got a little red X and an underline there. It says it's not valid. That's because they made a mistake in the partial, the checks for errors. Okay, in the syntax. It doesn't mean there is an error because this statement is still going to run. So if I run it, I mean, you can see the results down below. Already ran it. Well, I got to get back. Said this is the default table. Now I can run it. And there's the results. Okay. So even though this is showing like there's supposedly an error message, it's not. The intersect operator works. You can see intersect doesn't even get highlighted. I would imagine in a future upcoming micro release that that'll get fixed, but as far as I know, it hasn't been fixed yet. But the main thing is here you can see the tables that are the rows that are similar in those tables, because there's what's in each table. So you can see we've got A1 and B1. A2's here, it's not over there. A4 is in both. A5's here. A6 is over there. A7's in both. So it's only returning those that are common to both. And that's what the intersect operator does. Okay, now we're going to look at the minus operator. The minus operator, or if you're used to set theory, it might be called set difference. That might be more familiar to you. But it's used to subtract the result set obtained by one query from the result set obtained by the second query. Okay? In other words, we say the minus operator will return only those rows that are unique in only the first select query, and not those rows that are in common to both the first and the second. Okay? Now, this operator is not commutative, okay? Because r minus s will not equal s minus r. Okay? Here you can see the operator. It's not a special operator. I think I probably still have it over here, maybe. Yeah, maybe. But this is just the normal dash, so it's not something, one of these other operators that you might need to use. So let's look at an example here. If we wanted to list the Social Security number of the employees that do not have dependents, okay, this is how we'd go about doing it. Okay, so I'm getting in result set 1 here, I'm getting the Social Security number of all employees. In result set 2, I'm getting the Social Security number from of the employees from the dependent table. And then I'm simply subtracting where I have all the Social Security numbers, I'm subtracting the Social Security numbers of those who have dependents. And then I end up with just a list of the Social Security numbers for those employees that do not have dependents. Now, to see this in relational algebra, there is no direct implementation of this. Okay, there is no minus operator in MySQL. In other SQL languages, there could be, like on Oracle or Postgres, but within MySQL, we have to do it like this. We're going to use a subquery and then use not in. You might hear this called an anti-join as well. So you can see out here we're getting the Social Security number of all employees, and then inside we're getting those just from the dependent table. So if I just run that inner query, I didn't set company back as my default database. So now I'll run that inner query. I included the closing parentheses, I think. There we go, finally got it. There you can see we actually have 3 distinct Social Security numbers in there, but we just go ahead and we get the whole list. Now from the outside, it's going to be getting all Social Security numbers from employee, but then it's going to be selecting only those that aren't in this list we just generated. So if we run the whole query, that's what we get, those 5 employees that don't have dependents. And that's how we use the minus operator, only it's not really a minus operator here. We have to use a subquery and not in. Okay, the next thing we want to talk about is what we call a Cartesian join. You might hear it called a Cartesian product or a cross join, I think maybe even a cross product. They all mean the same thing. And it means that you join every row to every other row in a table. And it's not very useful. I know they show a kind of an example in the book, and it almost is a good reason not to use this, because you get a bunch of spurious tuples. And that's really what you get, is just a lot of spurious tuples. It can also be very dangerous. And I'll give you a little war story here. When I worked at that financial services company, we were planning for a big conversion, and we did 10 mock conversions, meaning that we did for over the year and a half before we did our final conversion. We picked weekends and we did trial runs of converting, because we were moving a lot of our data to a third party. Unfortunately, Friday at 6 is when we started, and about Friday night at 4:30, we had a programmer run a query against our big database, and they did a Cartesian join by accident. Now our database was 4 terabytes. They were working with a couple of big tables. It was on an HP Superdome, which at the time was running on 3 partitions, and each partition was worth $250,000. So it wasn't like it was running just on a little bitty cheap machine. Okay, so that programmer started their join about 4:30. It was around 8 or 8:30 at night when we were finally able to log into the server to kill the query, it took that long because it just busied up that database server so much. Okay? And it's really easy to do, unfortunately. You know? Now there is the proper syntax for doing it in SQL. Okay? Select star from employee cross join. You notice I didn't even show you the relational algebra because we're not going to have any problems on that. Okay, if I run this, we'll see. See how John Smith is related to all dependents. So is Franklin. So is Joyce. Okay, just really doesn't make sense. Okay? So why am I even talking about this? Because I would bet one or more of you, when you're writing your SQL statements, are going to do this by accident. And let me show you why. Okay, so far we haven't really talked about. I'll just do star just like the other one instead of listing some names there. I'll just put the star up there. Okay, if I run this now, okay, this is what we call a join condition. And if you notice, that's the primary key in employee and the foreign key over in the dependent table. Okay? And that's what we use to create our join conditions. So if I run this now, what did I spell wrong here? Dependent. How about instead of dedendant? Oh. Dependent. Let's try and get my spelling right. There we go. So John's related to his dependents, Franklin to his, and Jennifer to hers. Okay, that looks pretty good. Now when I say that you might do this by accident is, a lot of students will forget this join condition. And if I forget that join condition, look what happens. I get the same output as a cross join. Okay? So it's not really something you want to do. Notice when I had 56 rows from the cross join I did, I just had 56 rows returned from this join without a join condition. With the join condition, I only got 7 rows back. Okay? So if you run a query and you're thinking, wow, that is just a lot more data than I expected, make sure your join condition is there. Okay? So that wraps up what I wanted to talk about that Cartesian product. Not very useful all on its own. You get a lot of spurious tuples, and it can just waste a lot of resources as well. Okay, now we're going to look at join. Okay, and what join does is it allows us to process relationships between tables. If you remember, when you created the ERD for the company database, you formed relationships. They were formed based on a foreign key referring to a primary key. Right? That's how we formed those relationships. That's how those lines appeared when you made those connections. Right? So, where you take advantage of those relationships in our relational algebra and our SQL, because single table queries are great, but you don't get the information you want most of the time. Most of the time, you're going to be working with more than one table. So if we look at that syntax, notice these are attribute names down here. We've got pk equal fk, or it could be fk equal pk. It really doesn't matter which side the relation with the foreign key is. This pk is with that relationship. This fk is with that relationship. In this other example, the fk is in this relation, pk is in that relation. So that's just a little bit about how the syntax works. And again, it is to join tables together, and it will do it on an equality condition. So let me give you an example here. If we want to list the names of employees who have a dependent, this is what we can do. So we go ahead and we say join employee to dependent. Now it's going to be an equality condition. A lot of times we'll see a Venn diagram drawn for this. And what we're doing is, if we have this is the employee table. This is the dependent table. And what we're returning on were their matches. Now actually for the dependent table, everything would fall in there. If we were looking at one of those join tables that we have though, if we did that here, we would put, what would we have? we'd have table A, table B. Okay. We would have 3 in here that are the same because we got A1, A4, A7 the same in both of those tables. Okay. I would have 2 of the tuples out here on both sides because A2 isn't in table B, neither is A5. Same thing over here. A3 isn't in A, A6 isn't in A either. Okay. So our joins, when we do this join, we're only looking for the things that are where the join condition is equal. Okay. Now in our relational algebra operators here, I have them. And this is the symbol for just the plain join. Okay. It also has some synonyms. It could be called an inner join, a theta join, or an equijoin. They all mean the same thing. We're doing an equality condition and only pulling the tables that are in, are the tuples from the tables where there's a match on that join condition. So that's how that would look. And if I want to go ahead and do this in SQL, I would do it like this. Let me go back here, open up another one, and I would do this. Company's the default, so this should work here. So I'm getting employee first and last name from the employee table, joining it to the dependent table on the employee social security number equal to the employee. This is in the employee table, and in the dependent table, the employee social security number. And if I run that, there we can see those are the folks that have dependents. Okay. So that's how the inner join works. Okay. It is an equality condition. Okay, now I want to look at some outer joins with you. Okay. And we have 3 types of outer joins. We have a left outer join, a right outer join, and a full outer join. And you can see those symbols here. They're very similar to the inner join. Okay. Left outer join has those little bitty lines sticking to the left. Right outer join has a couple little lines sticking to the right. And a full outer join has those little lines sticking off the join symbol on both sides. Okay. So let's talk about what these joins actually do. Okay. So I already said an inner join between those would just return those 3 columns. Okay. And I think I have that here. Here's an inner join with those columns. I'm going to run that, and I got to make it the right. Sorry about that. Set the default schema there. Run it. And there we get. Okay. Those are the rows that are common to both tables. So if we look back over here, those are those 3 rows that we talked about. Now, if I do a left outer join, the table that is to the left of the join symbol will return all rows. So if I have table A to the left of the join symbol, so I would do, let's turn back on the drawing here. If I did table A, and then I did, and I'm not a very good artist here, that's supposed to be a left join, and we'll do it on A column equal A column, and then have table B. I will return every single row from table A and those same 3 matching rows. Okay. Now, A2 does not have a match, so for the B column rows, it'll show null. Okay, for both of those attributes. Same for here. We'll see some nulls. Okay. But I will get every row from here. So if I look at how we can do that in relational algebra, notice what I'm doing there. I just said left join. Other than that, it's exactly the same as the inner join. I just put left join there. When I run this, there you can see I got every single row from table A, and those rows that did not have a match, there's nulls that show up there. Let's look at something that might be just a little more practical than just something abstract like those tables. Let's go into our company database. Let's make it the default. Now I'm left joining employee on dependent. So we know we have some employees that don't have dependents. So we're going to see them. We'll also get the employees that do have dependents, and they'll have the dependent name next to it. So when I run this, There we can see John had 3 dependents, Franklin had some, Joyce, Ramesh, and James didn't. Jennifer did, just had 1. Abner and Ahmed and Alicia had no dependents. So that left join pulls from pulls everything from the table that's to the left of the join, okay, and only the matching rows from table A. Now a right join, very similar, okay, except this time I'm pulling all of the tuples from table B and the matching tuples from table A. So if I run this, oh, I gotta set this as the default schema again. I'll run that. There you can see I got all from table B and the matching ones in table A, and if there's no match, I get the nulls over there. So we've looked at left, where we get all from table A and the matching rows. We've looked at a right, where we got all from table B and the matching rows in table A. Now a full outer join, we just combine the two. Okay? We will get all rows in both tables returned. If they got a match, we'll have attributes in both, across the whole result set. If not, we'll have nulls in the appropriate place. Okay? Now, unfortunately, MySQL doesn't give us a way to implement this directly. Okay? We have to use a union to do it. So we take a left join, a right join, and union them together. And that will effectively give us a full outer join. So when I run that, there you can see what the result set looks like. If I can pull that up a bit so you can see them all. We've got the rows that match. Okay? And if there's no match, we get nulls for the appropriate ones. So that's the discussion about the different sorts of joins. Okay? We briefly looked at that inner join again, but then we looked at left outer, right outer, and a full outer. Okay? And that wraps up these outer joins. Okay. Now we're going to look at something called the natural join. Okay? And this, similar to a Cartesian join, although it's not as expensive in resources that way, this can be really expensive in terms of employee time trying to figure out code. I don't recommend you ever use a natural join. The syntax is simply this: relation star relation. And you'll get attributes from both. Right? And the way it'll form the join condition is on columns that have the same name. That's it. Okay? So if you don't have columns that have the same name, you can't even use a natural join. And if you do, you can use it, but your primary key, foreign key that you're trying to join the relation, make that join on, those might not be the only columns with the same name. Okay? So you can really get weird results. It makes maintenance of code so much harder, and it's just something I don't recommend you ever use. I'll give you some examples of it. Okay, so let's look just at the relational algebra. Okay. There we're natural joining department to department location. We're going to get the attributes from both tables, almost all the attributes. From the second table, you won't have the columns that have the same name that are in the first table. That's really the only difference. But if you look at this, okay, I don't know what I'm joining on right now. I mean, I'd have to go look at the tables, figure it out, where's the key in the foreign key, primary key, and figure out what's going on. And really, we're looking for columns with the same name. Right? So imagine you wrote the statement, and 9 months later, you come back and want to work on it, and you're going, oh my gosh, I did a natural join department to department location. First thing you're going to have to go do is, okay, let me go find the ER diagram and try to look that up, which is not very good use of time that we're paying a programmer to do. Right? So I don't recommend that you ever use this. Now, to see it in action, it looks like this. If I run it, I get everything. If you notice, these first 4 columns are from department, The last column is from department location. The D number that was in department or in department location was not returned. It had the same name as this D number, so there's no real reason to have it. If I'd done an inner join, I would see that on their D number. And that's really all the difference in the results. Okay? We just don't have duplicated attributes in the results. But the cost of those duplicated attributes, in my opinion, is far better than writing the natural join and possibly joining on attributes you didn't mean to, or just making it difficult to maintain the code. Okay, so that's that natural join. Okay, the last operator we're going to look at is divide. Okay, and this division can only take place, you're going to divide one table into another. Okay, so if you have table A that's going to be divided by table B, table A has to have more columns than table B. Okay? And what it allows for is the listing of rows in table A that are associated with all rows of table B. Okay? So let's look at an example of what we're going to do here. All right, from what I just said, table A is R, table S is table B. So we're going to divide R by S. Now R has more columns, so we can do it. So what we'll be looking for is instances where B has the same value and has all values of A associated with it. Okay? So if we look here, we can see B1 has A, 1, 2, and 3. Okay? That's in our results set. B2, well, it only has A1 and A3. It is not in the results set. Same for B3. It's got 2, 3, and 4, A2, 3, and 4. Doesn't have A1, 2, 3, so it's not in the results set. And then finally, B4 has those. And that would allow us to divide table R by table S, resulting in table T there, or the result set table T that has just B1 and B4. Okay. Let's look at an example of a division in relational algebra. Okay. If we want to retrieve the name of employees who work on all projects that John Smith works on, it's this going to return John Smith as well, but we're going to have to select where the first name's equal to John, then last name is equal to Smith. Now I'll give you a word of caution here. You don't know John's social security number. So if you'd pull up this handout and go in and say, oh, there's John Smith's social security number, and then just type in where SSN is equal to that 1, 2, 3, 4, 5, 6, 7, 8, 9, you will lose points. Nowhere in this problem did you give that answer. Okay? Or see that, not the answer, see that social security number. So how'd you get it? You had to do a manual intervention. Okay? If that's the case, why don't you just figure everything out and just project the names? You could just project John Smith. Okay, that would not be what we wanted to do. We want to write, so given some input right there, we can create a select condition from that. We're selecting John, where it's equal to first name, last name equal to Smith. We're getting the social security number when we do that, but we don't know it. Okay? So in this case, we're getting John's row, his tuple out of there. We're now joining it to the works on table based on the match of the social security numbers. That's going to give us all tuples from the works on table that John worked on. Then we're projecting the project numbers that he worked on from that. Okay. So now I have in the table that's going to be doing the dividing, okay, so if we call that table B, table A that's going to get divided by, I just have a Pinot in there. Okay, and it's going to have as many tuples as John worked on projects. Then from works on, I just select the ESSN and the Pinot. And this will be for everybody. So what's it going to do? It's going to look and see where this set is the same for any ESSN. And then that'll be the results. Okay? And that's what I'm doing in this P&O here. I'm dividing the entire list of Social Security numbers and P&Os from WorksOn, dividing it by Smith's P&Os. That's going to give me just the Social Security number there. Okay. If I want to get the names, I'm going to have to join that Social Security number to employee, and then I can project the names off of that. Okay. So there's an example of how we could use division to find out who worked on the same projects that John did. And that wraps up the operators. Now we're going to do a little bit of practice. All right, now we're going to do some practicing. This will be similar to the practice that we did at the end of last video. And I encourage you all to work through these before you look at the answer. Okay? Get the experience doing this. Write it out, type it out in your on your computer so you can get the subscripting correct. Because if you don't practice now, the first time will be on the assignment, and I would almost guarantee you're going to make some mistakes. So go ahead and practice these as we go. Our first one here, write the relational algebra statements that'll list the name of any project located in Houston. And you're going to have to name that column project name. Okay, so go ahead and hit pause and work through this. All right, let's go ahead and see the results of this. This is very similar to what we worked on last week, in the last module. Okay. It's a single table query that we're doing. We're selecting from projects where the location's Houston. Okay. And then from that result set, we're projecting the project name and then renaming it. Okay. So that's the first practice. Now for the next practice. I want you to use the intersection operator and then write the relational algebra statements that are going to list the first and last name of any employee who has worked on the product X and the product Y projects. Now before you start on this, I want to ask you one thing. Could I ever get this where P name is equal to product X and product Y? Would that ever be true? The answer to that is no. P name is an atomic value. It can only be equal to one thing. If we look here in the company database, we have the P names. They only contain one value. And we look at this, evaluate at one tuple at a time. So the P name will never, ever be equal to two values. Okay? No attribute will. So keep that in mind when you're working on this. So go ahead and hit pause and see what you come up with. Okay, let's go ahead and look at the solution now. This is a little more complicated than what we worked on. Okay? Remember, to be able to use that operator, the intersection operator, we have to have union compatible relations. Okay? And let's see what I did here. So if we look at here, so if I want to know the employees that have worked on product X, I'm going to have to select from here on product X, join to WorksOn based on the P number, and then I can list those Social Security numbers. Same from product Y. I can select product Y, join based on the P number, and get those folks that worked on it. And that's pretty much what I'm doing here. I'm selecting the product X from project, joining to WorksOn, and then projecting the Social Security number. Then I do the same down here, and I get result 1 and result 2. Now I'm going to get the product Y employee Social Security numbers, those that worked on product Y. So that should actually be there. I was making some changes, didn't make that. That's PY, that's PY. And then now we have result 1, which has the list of Social Security numbers that worked on product X, sorry. And we have a list of Social Security numbers in result 2 that worked on product Y. I intersect those together. Okay. I will now have the list of Social Security numbers in result 3 that worked on both product X and product Y. because in result 1 I had those with product X, result 2 product Y. I go ahead and intersect those, and I only get the ones that match, and those are the ones that worked on both projects. Then I go ahead and I have to join to employee so I can project the names. Okay. So that's practice 2. Okay? And we're using the intersection operator to list the names of the employees who worked on both of those projects. Okay, now I want you to go ahead, using the minus operator, write the statements that are going to list the first and last name of any employee who does not have a dependent. Okay, so go ahead and hit pause and work on that. All right, here's the results for that, or the solution. Okay. So I'm selecting the Social Security number for employee, selecting it from dependent, subtracting it out, joining back to employee, and projecting the names. Okay. Keep in mind what is showing up in all employees. I only have Social Security number, employee with dependent, just a Social Security number, and result 1, just a Social Security number. Once I join it to employee, now I've got everything from employee, all the different attributes, and now I can project those names. Okay, so let's do another practice here. Let's get another problem. Let's do this. Okay, using inner joins, write the statements that are going to list first and last names of any employee who's worked on the computerization project. So go ahead and hit pause and work on that. Okay, here is the solution for it. I'm selecting, and that's normally when I see something that says, oh, here's where I'm going to have a select condition. I try to do that as early as possible. Do that. And if you notice, the last statement usually is some sort of a project, unless what we did before happens to have the solution. And sometimes it does, especially working with aggregation. Okay? But here you can see I selected the tuples from the project, or the tuple from the project table where the P name was computerization. I joined it to works on. Okay? Then I joined it to employee, and we kind of have to go that way. If we look at our EER diagram, I'm starting in project. I want to find the employees, so I've got to go through works on, and then from works on, I can go use the SSN to get the names of the employees. And that's what we're doing there. Okay, let's do another practice now. Let's do this. Write the statements, list the names again of employees who charge hours to a project. Additionally, I want you to total up those hours that were charged to all projects. So if the employee charged hours, I want to see the total number of hours. Okay, and we got to use appropriate names for the columns. And again, those should be names that could be used as a variable in a language like PHP or Java or C++. Okay. So go ahead and hit pause and work on this one. Okay, and here is the solution for this problem. Okay. Well, the first thing I do, I want to make sure I don't include the person in our database who charged the null hours. Okay, and I think that was James Borg. So I want to make sure I don't include him. Look at what I use for that not equal sign. It is the not equal sign from here. Okay, that one right there. So make sure if you're doing a not equal, you copy that into your onto the document you're creating. Okay. Then I'm doing some aggregation. I'm summing the hours. Okay. From the known null hours, grouping it by the Social Security number. That's going to give me, for each employee, the total number of hours that they have. Okay. I've got the employee Social Security number there, so now I can join that to employee, and then go ahead and project the first name, last name, and the total hours. Okay. So that's the solution for this one. Let's go ahead and look at another here. One last one. I want you to write the statement and list the names again. If they have names of any dependents, list the dependent names as well. Okay. So I'm listing the first and last names of all employees. That is a hint that you're going to have to use an outer join. And then another way you can look at it, if the employee has dependents, list those names as well. That's implying that there's probably going to be employees without dependents, but we still want to list them. Okay, so you're going to have to use an outer join in this one. So go ahead and hit pause and work on it. And here we have the solution for it. Okay. We want to do, since I put employee to the left of the join symbol, it's a left outer join. If I had an employee to the right, it'd be a right outer join, but I'm doing a left outer join and an equality condition there, the social security number equal to the ESSN, this PK equal to the foreign key. Okay. And I'm getting all the attributes from both, and then I'm just projecting the names. And there will be employees there that don't have any dependent names. We have 5 of them. Okay. So that's the practicing done for this chapter. Okay. And we pretty much wrapped up the chapter now. All right, good luck with your homework.